Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everybody. I'm Stuart Townsley. I'm here this morning with my colleague John Nordlinger from University Relations here in Microsoft Research, and we've invited to speak today Paolo Virginian from Evolution Robotics. Paolo is an emerging friend, I hope, of our robotics initiatives, and is very well respected in the field of robotics. But it's a little bit more than robotics. He's actually going to frame his talk a little bit wider than robotics and talk about the vision technology at Evolution Robotics. So please enjoy the talk. Paolo.
Thank you very much, Stuart. It's a real pleasure to be here and share with you what we do at Evolution Robotics. And as Stuart already said, there are two parts to the talk. The first one focusing on vision and the possibilities of vision, and the second part focusing on robotics and what Evolution Robotics does in providing robotic technologies to companies such as Sony and so on. And the common theme is going to be vision, because we think vision is the future for many applications, but also for robotics. And I'll talk about that. So to start with, let me invite you on a journey to imagine the possibilities with computer vision. So imagine one day walking into my office and seeing the neat new book I have on robotics, and you like the book very much and you want to buy it. You take your camera phone, point it at the book, at one snap of the camera, the book is yours. Now, imagine you're shopping at Costco. You have all your grocery items in your shopping cart. You roll your shopping cart through the checkout lane, and all your grocery items are automatically rung up. And finally, imagine you're searching for your dream girl on an online dating service. And you do the search by showing the system pictures of your high school sweetheart. And it brings up people that are similar to what you were looking for in terms of characteristics. These are merely a few of the capabilities that we believe are possible with computer vision. And I think you at Microsoft understand the sexy applications of vision, and you have huge leverage, one of them being the Xbox, and now with the camera for the Xbox. We think because of the ubiquity of cameras and available low-cost computing, there is a huge new world around computer vision. And this is my personal passion at Evolution Robotics, to enable some of these applications. And I'll admit, my passion is not purely academic, although that's a major part of it. But it's also motivated by the huge business opportunity that I see right around the corner. And that's what I'll talk about today. And there is a large user base and very rapidly growing user base of cameras in applications such as webcams, camera phones, digital photography, and more. In Japan alone, there are 80 million camera phones deployed. So you have this very low-cost sensor attached to very capable computing and wireless connectivity to a sea of information on the web. That is a tremendous opportunity. And we think computer vision is a way to unlock that opportunity. Now, obviously, computer vision is not a new term. We have worked on computer vision for many years. But I think some of the key technologies are currently being developed. But the key is to be able to develop these technologies, computer vision algorithms that work in realistic environments, and do that very effectively from a computing standpoint. So there is no doubt in our minds that computer vision has this potential. Cameras are everywhere, hence they are becoming cheaper, and since they are becoming cheaper, they are becoming even more widespread. Cameras are versatile. They can be used for many different tasks. They can be used for face recognition, for things such as homeland security. They can be used for gesture recognition, for interactive gameplay, and so much more. So the key is to bring together these core technologies with the vast number of ideas we have about computer vision. And the pieces are coming together today. Here is a picture that, as we see it today, there is no shortage of ideas for computer vision. I don't need to convince you. You have been pioneering areas in computer vision. Computing is becoming available. Moore's law is fortunately on our side. Now we have mobile applications with pretty impressive computing capabilities and also wireless connectivity to a virtually unlimited back-end computing facilities. We have a really large user base, and this user base is growing rapidly and will soon eclipse the size of the PC user base. And at the same time, as we mentioned, cameras are really becoming cheap. We can buy cameras in significant quantities for less than a couple of dollars. This is an amazing sensor. And we are beginning to see some really promising algorithms. And I'll talk to you about some of those. And Evolution Robotics is a believer in computer vision, not only for robotics, but applications beyond robotics. And I'll give you a few examples. I was talking about imaginary applications just before, but I'll show you some of those applications are becoming a reality today. And Evolution Robotics is committed to providing the technologies to make those applications come true. So Evolution Robotics is a small company, startup company based in Pasadena. We were founded in year 2001. We have a team of very strong scientists with background in computer vision and robotics, control theory, AI. We have teamed that group of scientists with a set of very strong developers with commercial software development background, and a group of business people that understand the vision and the future for this. Our core capabilities are in computer vision and robotics. And I'll talk about those technologies specifically in this part of the talk and the next part of the talk. We have developed technologies that are built on Evolution Robotics technologies. We have products in the market such as the Sony AIBO that uses Evolution Robotics' visual pattern recognition technology. We have the Sharp Image robotic vacuum cleaner on the left-hand side that leverages some of our core technologies for navigation. And we have, for the education market, we have developed a product ourselves that allows you to access this kind of cutting-edge vision technologies in the high school domain to do interesting things and get excited about education through interesting applications. And then we have a software development environment to try to accelerate the development of applications for robotics and the like. So now let me talk about one of the core technologies, our visual pattern recognition technology, or ViPR for short. And this technology allows us to solve some of the fundamental vision problems. One of the fundamental vision problems, as you know, is the correspondence problem. Basically finding the correspondence between one pixel from one view of an object to the corresponding pixels in another view of the same object. That has been a very hard problem to solve. There have been many proposals of how to solve it. But obviously, the key to solving this is to be able to do it in realistic environments where you cannot really control the lighting conditions and other visual artifacts that can affect the performance of your system. And in addition, the other part is to do it effectively from a computing standpoint. So once you have the correspondence problem solved, that gives the solution to a number of other key computer vision problems, such as estimation of the structure of the scene that you're looking at. Once you have two or more views of the same scene and you can find a correspondence between the views, now you can do things such as triangulation or structure from motion and even pose estimation. So these are some of the fundamental problems that we need to solve. In addition, as you can see highlighted on the upper left view over there, the algorithm is recognizing a few objects. The Evolution Robotics logo up there. On the left lower corner there, it's recognizing the Dateline meeting room in a pretty cluttered view of the environment. And on the right side, you see it's recognizing the Yosemite meeting room, again, with occlusions and so on. These are realistic environments. The images coming in are not perfect. We do not have a perfect view of the object, but yet, if we want our vision systems to be used and useful for our users, they need to be able to work in such environments. So let me, as I mentioned, these are some of the key problems that this algorithm solves, and let me give you an overview of some of the fundamental steps in the algorithm. So ViPR is based on the so-called SIFT features. And I'm sure most of you are familiar with this. This is an invention by David Lowe from University of British Columbia. And the key idea is how do you encode these SIFT features, which are unique local features within small local patches of the image. You take those patches and encode a unique signature for those. So the circles you see distributed around this picture over here represent the position of these so-called SIFT features. So the algorithm basically finds the salient points in an image, and saliency defined as some unique structure and also uniqueness relative to the neighboring areas. So it's something that stands out. Once we have done that, then you can take a patch of an image around that point and encode the information there. And here it's basically grayscale gradient information. And we can encode that in a 128-byte descriptor. And 120 byte can contain many, many unique features. So once we have the descriptor for each of these features, and we have the position of these features relative to each other, now we have a model for recognizing this particular pattern for the Evolution Robotics logo up here, for instance. So the first step is extracting these SIFT features. And SIFT, by the way, stands for Scale Invariant Feature Transform. So it's both scale and rotation invariant. That means when we extract this unique identifier or descriptor for a feature, we encode the orientation of that feature by looking at the most dominant gradient in that patch. So now we will be able to recognize the feature even if the object is rotated. The scale invariance comes from the fact that when you start looking for those features, you do not look at it at that resolution of the image, but you build an image pyramid by downsampling the image several times and search for this feature on every scale of the pyramid. So now that if this object moves away from the camera, which corresponds to downsampling the image, you will find that feature corresponding to a low-res version of the image. So that gives you scale invariance. Now we have rotation invariance and scale invariance. Since we are using grayscale gradient information, the SIFT descriptors become very robust to changes in lighting condition, because we are looking for transitions of intensity values rather than the hard-coded intensity values. So the first step is extracting the SIFT features, the descriptors of each. Then you can save that information to have a model to recognize this pattern. The next thing is now you have these 128-byte feature descriptors, and you want to find the nearest neighbors. When you get a new image in, like the input image here, I want to figure out what is the nearest neighbor to that SIFT feature over here, for instance, and I have to look it up. And in this case, I only have one model, but in reality, I could have tens of thousands of models of objects. And I have to look in that sea of SIFT features and find the nearest neighbors for this. And here, you not only want to find the best matches, you also want to do it very efficiently. So we encode the SIFT informations in a structure known as the KD tree. And you can look up to find your matches very reliably and very efficiently. And the complexity is a log n complexity, which is beautiful. So now we have feature matching to find the nearest neighbors. Now, once we have found the nearest neighbors of the input image, then we can start looking to see which model they could stem from. And you can, one simple way to view it is that the object matching is accomplished by having the SIF features voting, each of the SIF features individually voting for the model that they belong to. And statistically, the majority of votes will vote on the correct model. One feature alone could vote basically arbitrary. It could belong to 10 different models. The same, another feature belonging to the same model would probably vote for the right model. And now once you have 2, then the probability of success is higher. When you have 3, it's significantly higher. When you have 4, you're close to 95% likelihood of a right match, correct match. And it increases exponentially. So the nice thing about that is, in some views, you might not see all the features. It could be because of noise, the feature descriptor looks different, or it could be because the object is occluded, is out of the field of view, and so on. The nice thing about this voting mechanism is that you only need to see a subset of, a very small subset of those original SIF features in order to reliably find a match. So now we have object matching. So you have the correspondence and you have object matching. On top of that, you could impose constraints such as affine constraints between the objects, the current view and the model that you're trying to match against. So you're looking at the cluster of features that match, and you can put that through a number of affine transformations and find the best match, which allows you to extract the orientation or the pose of the object as you see it now relative to the original image. So now, on top of object matching, you can even do pose estimation of the camera relative to that object or the object relative to the camera. So these are some of the fundamental steps. And I'm sure for those of you who have worked with computer vision, have seen a lot of talks on vision, and the presentation always works, the theory always works. So allow me to give you a quick demo of the algorithm so you get a sense for how reliable this algorithm actually works. This is my son, by the way, the best robot I've been able to create so far, but I can't take full credit for it. So here is a demo which actually is available on our website. You can access it online, signing up and downloading it. And let me turn on recognition here. So one of the things I usually say when I do these demos is that I didn't decide what the lighting condition should be here. And I've been involved in many demos myself, in university involvement and so on. And when the sponsor comes, you take them into your lab and you have the lighting beautifully set up and so on. And that's where you do your demo. Now, thanks for turning off the light, but I would have been able to do it otherwise as well. Actually, OK. So the camera I'm using is a regular webcam, USB camera here. It's a Logitech camera. And what the camera is doing is currently looking for the SIF features and trying to find a match against a database of objects I have down here. So there's a number of different objects. A number of them stem from pages on this Spot Goes to School book. So you see when I put the object in front of the camera, immediately it finds the matches to the SIF features, and the boxes that it draws are
Spot Goes to School by Eric Hill.
So that was
Spot
basically
Goes to
playing
School
a sound file.
by Eric Hill.
So you see, as soon as I put the book in front of the camera, it finds the SIF features, and it finds just a few. The original image, I'll show it to you. It has maybe 500 SIF features in the model. But when I put the book in front of the camera, it finds
Spot Goes
a
to
few
School
matches.
by Eric Hill.
And the sound file is just triggered by this recognition. When you recognize this page, just play this sound file. So it's obviously not doing character recognition.
Spot Goes to School by Eric Hill.
Let me turn off, well, let me show you some other pages.
What has Spot found inside the playhouse? What did you bring to show us, Spot? The playground is fun. Where's Spot? It's time to go home. The end.
So, as you can see, I'm not standing and trying to hold the object right in front of the camera. I'm holding it more or less casually. I can even have it upside down at an angle which is causing perspective distortion of the camera. You can see if you can see on the projection up there, there is some glare caused by these spotlights on the page. And obviously that causes that portion of the image to be not very useful, because in that area I won't be able to very reliably find the SIF features. I can put my hand in front of the object and cover parts of it. Obviously at some point it will fail, but you can see it's able to deal with significant occlusions on the object. So if I start covering up some of the most significant patterns, you see it latches onto other parts of the object. And at some point it starts becoming unreliable, because here it's actually only finding 5 features out of a few hundred. And the number of features that it's actually matching is what is displayed over here. So 30 features out of the original few hundred. So here are the original SIF features. So there's a few hundred SIF features, and the size of the boxes that you see here correspond to what scale in the image pyramid the feature was most significant. The line that you see going here corresponds to the dominant gradient of the SIF feature, which is used for rotation invariance of the SIF feature. So the size gives you the scale invariance, the orientation gives you the rotation invariance, and that's why I can have the object turned upside down. And just to give you an example, I could take a picture of the scene over here to show you how the algorithm trains on new objects or scenes. So I take one example that becomes my training image, and we could call it room, some arbitrary label on the object, and learn. So now the system basically built up this model. And you can see it's latching on to areas where there is enough information in terms of texture and gradient information. So the plain walls in the background don't have enough information, and it doesn't find any significant SIF features. So now if I point the camera in that direction, and you can see even though most of the image is out of the field of view, it's still able to latch onto the correct information and find the matches. And even if you had people move out of the way, since it only needs to see a subset of those features to find a reliable match, it's able to do that. So now, going back to my presentation here, and you can see here's another example with the same object that I demoed for you here. Changes in lighting condition, it's very good at handling those. Rotation and occlusions and scale. So this algorithm becomes really reliable. And when we talked to Sony originally and showed them this exact same demo here, there was no doubt in their mind this was a very powerful vision technology. They work on vision. And I have a lot of respect for what they do. And they have done really amazing things with computer vision for AIBO and ViPRGäó and beyond. But they could realize that this is an algorithm that we could actually deploy on 50,000 robots in arbitrary homes, and it would work. Now, our challenge was, we were showing the demo on a gigahertz Pentium, and their question to us was, we are running on a 200 megahertz MIPS CPU, and we are running face recognition and a ton of other software on it. You only have 40% of the bandwidth to run your vision algorithm. Can you do it? And we accomplished a 20 times speed up of our algorithm. So if you sit down and think about the algorithm, obviously there's always room for optimizations and so on. And we were able to accomplish a 20x optimization to really make this algorithm work in an embedded environment with very limited computing. And so the result is ERS7, which was released last November with our object recognition on it. And it's being used for 2 tasks. One of them is to make the robot really autonomous by allowing it to go back to its charging station and recharge itself. Because if the robot runs out of juice, it cannot be autonomous anymore. So that's number one thing. So it uses our pose estimation to calculate the orientation and pose of the robot relative to the charging station, walk back and sit on the charging station. The second part, which is to me ironic, is to use vision for human-robot interaction. So they have a deck of 15 flashcards, each of them representing a command. And you command the robot by flashing one of these cards to it to tell it to go back to charging station, dance or play or take a picture and so on. And that's what the robot does. Now, I said to me, it's ironic because we have worked on voice recognition and we had made a lot more traction on voice recognition compared to computer vision. But here, they are relying on vision for human-robot interaction rather than their voice recognition, which is an interesting development for the computer vision community, I think, overall.
The algorithm that's running on the iBot now was running the optimized algorithm running on your laptop now?
The one I'm running here is the old version. It's not the optimized one.
Okay, and the second question is, the face rec stuff that AIBO is doing,
It's not using our algorithm.
why not?
So for face recognition, we do not recommend ViPR for two reasons. Number one is that on faces, you don't have enough texture. That's one reason. The second reason is that in the current implementation, we are assuming we have a fixed configuration of these features. That means you're looking at a rigid object. If you start moving these object features around, which happens on a face because of the facial expressions and so on, you're talking about the deformation of this. We will not be able to recognize it in the current implementation. But I would not say that's an inherent limitation of this algorithm. That means if you relax your constraints, currently we have this affine constraint for recognizing objects. If you relax your affine constraint and put an epipolar constraint on top of it, you will, I think, be able to do face recognition. But at the same time, I think face recognition algorithms, dedicated face recognition algorithms, have come a very long way, and I would wonder whether this algorithm would be really able to compete with those, or whether we should use those algorithms.
How well does the face rec algorithm work?
I don't know. I don't know. Our algorithm will work for faces. I mean, if you train it on yourself that same day, it will work maybe about 60–70% of the time. But the current face recognition algorithms with limited set of people will be closer to 90%. So now, I talked about some imaginary applications. I talked about the core technology that allow us to make those imaginations a reality. So one of the areas that we are working on is allowing the checkout people at a grocery store to be able to check out your items by just having you roll out your cart across the checkout lane. I'll show you a system that we have actually implemented that does that. Another one I talked about is being able to point your camera to an object and take a picture of it, and that can connect you to some information on the web. So with a camera phone where you have a camera, you have computational power, and you have wireless connectivity, now you can make the physical world hyperlinkable. You can basically annotate any object in the real environment by pointing to it, clicking on it, and query information or take you to a different location. And for playing, I think you have at Microsoft the leverage. The leverage is that you have Xbox. And what can we do with Xbox and the camera on the Xbox? To leverage technologies such as ViPR to make the gameplay so much more interesting so that you do not need a joystick anymore, but you can physically interact with the game. So the clippable world idea is basically augmenting the real world, as I said, with hyperlinks. And I can show you a demo afterwards, whoever is interested, after the talk is over, to show you that we can actually take pictures of objects that we have trained the system on already with this camera, and it will tell us what the object is. Now, the next step is that we should work together to take this technology, the user base, and make applications that our users want. And that, we think, is real today, and we'll soon see applications such as this coming out in the market.
Was that a set as well?
Yes. Yes. And I talked about interactive games. You are a much better judge of saying what we can do with this kind of technologies for Xbox. And finally, the retail loss prevention problem. So it turns out, I mean, when we started a robotics company, we never knew we were going to end up here. We developed some core algorithms for a vision for robotics because we think vision is the right way for getting robots to perceive their environments for many tasks. But we came across a problem with the retail store. U.S. retail market suffers from a $1.5 billion loss annually of items that go under the cart, the big rack under the shopping cart, and they make their way right in front of the checkout lady out of the store without getting paid for. $1.5 billion annually. Another way to think about it is you have $15 per lane. That's one item, one big item per lane that leaves the store per day. You have 10 lanes per store. That's $150 per day per store. Multiply that by 350 days and multiply that by 2,000 or 2,500 stores in a chain. You end up with a problem that's close to $100 million just for one big supermarket chain. That is a huge problem. And they have been trying to solve this using many different techniques. And I'm sure you can, off the top of your head, think of RFID tags as one approach. And we can have a discussion on that. That's not real for the next 5 to 10 years. So we have implemented LaneHawk. This is an article that picked up our press release on LaneHawk and made a nice cartoon over it. So now, if we are able to detect items by just having a camera in the checkout lane, looking down the bottom of the basket, when you roll your cart by, it will scan it, detect the objects, and automatically ring them up. Now you're capturing revenue and putting it towards your bottom line that otherwise would have been lost. And I guess you are familiar with this picture of taking a bite out of crime, and that's what Evolution Robotics is doing. So here's a video. I think I'll mute it. So here's a video that shows the actually very earlier prototype of system that shows basically the bottom of basket problem. It's called the BOB problem, bottom of basket problem. And basically here is the problem where you have these big items that go under the rack over there. You would implement this camera flush mounted to the side of the checkout lane, and when you roll your shopping cart by, it will basically, actually it has several filters. One is triggering based on the flow of motion of the cart, and then triggers the object recognition. The object recognition has a database of several hundred items, and then it recognizes it and actually can identify all the items and automatically ring them up. As a last resort, you have the checkout person has to approve whether the objects were correctly recognized or not. But still, we have to have a very high confidence of recognition and very, very low false positive rate. Because one problem is that if a system starts triggering false alarms, then typically the users of those systems do not pay any more attention to the system. It's like your alarm, security alarm at your home. If it goes off every day you're at work, and every time you check up on it, it was a false alarm, you start ignoring the system. And the same thing has happened in this area as well. So this is concluding this part of the talk, and I'll talk about robotics and vision applications for robotics. So we think vision is extremely powerful. We think the pieces are coming together. We have computation available. We have very low-cost cameras. We have tons of ideas about applications. And now we have some technologies, such as ViPR, that give us an insight into how we can put these pieces together to build applications. And the LaneHawk and cell phone applications and camera phone applications are just a few of the examples, which in my opinion represent the tip of the iceberg. And I think other areas of using cameras for game interaction and so on are other areas that we think will be very interesting to pursue. So by that, I'll conclude this part of the talk and start moving on to the next one. And please feel free to ask questions.
Just a question on ViPR that went into the Sony AIBO. Did that represent any compromises to your algorithm, or is the performance in AIBO consistent with the performance we see on the laptop?
The version that's out in the market today is consistent. That means the optimization we did not compromise the reliability of the algorithm. Now, but we squeezed every single cycle out of that CPU to get it there. To get to the next stage, which we are doing actually currently, there will be compromises. You will have basically knobs that you can tweak to trade off speed for reliability of the algorithm and so on. And for some applications where you have control over some of the parameters, such as in this case for AIBO, you know the patterns you're looking for. you might be able to get away with those tweaking that go on.
What frame rates are you getting for your SIP detection on the AIBO?
So on AIBO, they are running at 320 by 240 and about 5 hertz.
So you mentioned you use a nearest neighbor algorithm with KD trees. I wonder if you can mention a little bit about the scalability of the database. So as you get to the thousands and hundreds of thousands of objects to recognize,
yes,
how well is the algorithm going to actually do?
Okay, so in terms of computation, it scales logarithmically. So we have even validated that empirically rather than just looking at the depth of the KD tree. In terms of reliability, when you go to hundreds of thousands of objects, each of them, say, have average of 500 SIF features on them, then you have a huge KD tree. And the uniqueness of the SIF features starts basically they're becoming less and less unique because you're basically populating this space, this 128-dimensional space, with so many features that there will be clusters that are very close to each other, and now the SIF features are not that unique anymore. And so we are actually working on scaling in that direction, and there's a number of tricks that you can look at, and we are exploring those right now. So the current experiments we have done is up to 10,000 objects, and their recognition rates and so on do not suffer significantly. When we go to hundreds of thousands of objects, then we start seeing some limitations that we are working on right now. So you are free to ask any questions later also. I'll shift to the next part of the talk, which is focusing on robotics, or robots for the masses. So our vision in this area is to have a robot in every home and workplace. So we want robots to be able to do some work for us, and you have already seen robotic vacuum cleaners that do some of that work. And there are many other opportunities. We want robots to entertain us, and we want robots to help our elderly, which is a very significant problem in the civilized world, both in US, Japan, and Europe. The elderly population growth rate is much faster than the people that have to take care of them. So it's a very nice application for robotics if we can solve some of the key problems. But obviously there are barriers, technology barriers. Robotics is a relatively new field, and there are a ton of things that we have to deal with. And so apart from the fact that robotics has really hard challenges, and since it's multidisciplinary, it goes across many different fields. And when you combine the complexity of all those fields together into one system, it becomes even more challenging. But on top of that, and this is my own perspective from working at Evolution Robotics, having worked at space exploration at NASA and university research and so on, cost is a major, major, major constraint. And I'm sure you can appreciate this coming from a commercial company that also builds consumer products and so on. But when you combine the challenges of robotics, which are already really hard to surmount, with constraints, tremendous constraints on cost, it becomes so much more challenging. And I'll give you an example of that to put this in perspective. Reliability. In the robotics community, we have been talking about real-world robotics for many years. And what that has meant is that we can have our robots work in the lab rather than do simulations. But now it's a real-world robotics because I have a robot that will get deployed, sold in hundreds of thousands of units per year. So it's going to go in hundreds of thousands of homes that I have never seen. And we know our mathematical tools or formal tools are not powerful enough to capture a model for the world yet. So what do we do with our techniques so that they will work reliably? And one of the examples was ViPR, computer vision that can work under varying lighting conditions and artifacts. And then the final and maybe the ultimate challenge is living up to the expectations of the customers. The consumers have been seeing a lot of Hollywood movies and so on, and their expectations are very high. So combining those three together makes the technology barriers even harder. Just to give an example, imagine a consumer robot that retails at about $200. You can think of the EVAC or the iRobot Roomba as an example. It retails at $199. So for a company to have a business proposition out of selling a product at $200, the cost for manufacturing and putting that product on a shelf to them cannot exceed more than 1/3 of the retail price. So in this case, let's say $70. And that includes production cost, all the parts and components, packaging, manuals, shipping from China to be on a shelf at Sears so that you can pay $200, take that box with you home and unpack it and have fun with your robotic product. So out of those $70 are all these things. A subset of that is obviously the hardware components. Now, for a robotic vacuum cleaner, the main components are vacuuming components. So when you strip out all those parts, then you end up with the budget for the robotic components. And robotic components are at least the sensors, actuators, and some processing. And there you have a budget of maybe $30. So imagine a robot at $30, and it has to be reliable. You're selling hundreds of thousands of units of this. If you're not successful, they're going to return it back to you, and you have to eat the cost. So imagine solving some of the hard robotic problems: obstacle detection and avoidance, localization and mapping, human-robot interaction, path planning, and so on. Imagine solving those problems. And now imagine solving all those problems at $30 cost. That is a challenge. And that's a challenge that we have to live up to make the consumer robotic market to propel. So we talked about applications, and obviously you can ask, where are these robots you're talking about and so on. It's emerging. We believe it's going to emerge. The question is how fast, and we think over the next 5 to 10 years it will become a very large market. Right now, Roomba represents probably the bulk of the market because I think what they have done very well is to find the right price-performance ratio. They have a robot at $199, and it does an okay job for a $199 product. At least 300,000 customers believe that it does. So it doesn't matter what I mean or what I think. That's what the customers say. It's a product. Because prior to that, we had the first robotic vacuum cleaner was put in the market by Electrolux about 5 years ago, the Trilobite. Very nice product. You look at it, you will appreciate the design, the industrial design, the sensors it has, and the performance and everything. Beautiful. But it's $1,500. So the price-to-performance ratio there doesn't seem to be right, at least if you ask the consumers. So making the right trade-offs is one of the keys here, obviously, but also solving the technologies at a low enough cost so that you can build a robot and sell it for $200 is key. And there are a number of other applications. Some of them are very visionary, like the Honda AIBO, which we think is more for building an image for Honda rather than any commercial application of the AIBO. But the technologies that they are developing for AIBO are tremendous. And someday these technologies will be embedded into a number of different areas. So as we found that our vision technology can be embedded in cell phones and for loss prevention in retail, there are a bunch of technologies from AIBO that in the future will be embedded in cars and motorcycles. And I think that's one way that we will see robotics evolve. And to talk about the automotive industry, I think I'm very impressed by what the automotive industry is able to do, because in many ways what they have accomplished have a lot of similarities to what we have to do in robotics in terms of reliability of the system, driving for thousands and thousands and thousands of miles without needing any service or breaking down, the interaction with an unknown environment, vibrations, and so on, and the complexity of the system. A lot of mechanical, electronical, software components, and so on. And those guys are actually gradually putting more and more autonomous capabilities on the car. So you have the cruise control, and then you have ABS and traction control, and now you have distance keeping, automatic parking assistance, and the car will one day become the ultimate robot, I think. And if there's an industry that can pull it off, it's that industry. They know their trade very well. So now, I talk about the applications, I talk about the technological challenges, and let me start talking about some of the technologies that Evolution Robotics has developed. So here's a crude comparison between standard software development, developing software applications for desktop or palm-top computing and so on. And on the right-hand side, we have the analogs in robot software. So on the left-hand side, we have this, the basic units we have is the instruction set of the CPU. And we have built abstractions on top of that to make it more and more easy for our developers to develop applications without worrying about what is the CPU I'm working on, what is the instruction set, how do I load this data into the register, and all these things. So for robotics, one way to look at it would be that you need some core capabilities for enabling the robot to interact with its environment, to move from point A to point B. That's a simple primitive instruction. To follow a target, to grab an object, to move an object, and so on. So you could view those as the instruction sets. On top of that, you need to have an operating system. Obviously, you need a computer that is coordinating the activities of the robot. So there's a lot of operating system components that are generic between general computing and robotics. But on top of that, you need some specific, robot-specific architecture for developing the algorithms and coordinating the activities and so on. And I'll talk about the components and the architecture. And the architecture in robotics specifically is important because you're, again, dealing with a very complex system consisting of many, many modules. And even though the components, the basic components are key, but integrating this into an application typically takes a long time. I mean, even if we are handed the core component technologies for navigation and human-robot interaction and so on, putting all those into an application, if you do not have an architecture, becomes challenging. Because you have a bunch of resources that are hungry for, bunch of modules that are hungry for resources, and they have to fight for those resources. For instance, my obstacle avoidance tells me you have to turn right here because you're getting close to an object. My module that wants to grab that object is telling me, no, you have to go straight forward. So you have to do conflict resolution, and there's tons of decision making and so on. So having an architecture allows you to do that more rapidly. So what are the key components? And you can use, I use my 4-year-old son as inspiration for this. So the first thing you need to do as a robot is to be able to get around. If you are mobile now, you can do a lot of damage. That's why what I discovered with my son. My wife and I were always saying, oh, he's not walking and yet, and so on. And as soon as he started walking, we discovered how hard it is, because now you have to watch him. He can walk, but he's not capable of, for instance, going down the stairs and so on, so he can damage himself. So the first thing is to learn to walk. The second thing is, when you have learned to walk, is interacting with the environment and with people. So human-robot interaction. And then the next thing is robot interaction with the environment. So in case of my son, he would grab things and throw them. And he would practice that for a month or so, and then he went to other skills. And then social skills are the next, so robot-to-robot interaction and learning. So we start at the top, and we say that for consumer robotics to take off, we need to have some navigation components. For vacuuming is a good example. I mean, what a vacuum cleaning robot does is a vacuum that is mobile. So the vacuuming technology is perfected already. What we need to add there is mobility, so that the vacuum cleaner can move around and manipulate the environment. So in one way, you could say the manipulation part, the robot environment interaction part, is a ready technology. Vacuuming has been perfected for many years. What we are adding on top of it is navigation and mobility. So Evolution Robotics focuses on 4 major areas. Number 1 is vision, and the reason being, as I mentioned before, cameras are really cheap. In theory, they are versatile and can be used for solving many different applications. They can be used for navigation capabilities, they can be used for human-robot interaction, and they can also be used for manipulation of the environment in the future. The next one is navigation, key capability, and then interaction. And then the blue box underneath all of it is the foundation, which is the architecture that allows you to glue all these things together in an effective way to build applications. So today, I already talked about ViPR, so I'm going to talk about some other technologies. So number 1 is vSLAM, which stands for Visual, Simultaneous Localization and Mapping. what that means is for a robot to be mobile and effectively mobile, one of the key problems or challenges in robotics has been to figure out where the robot is. So it's GPS-like capability. The robot is indoors and it needs to know where it is. Because once I know where I am, I know how to get to the locations I want to go to. And this has been a tremendous challenge for the robotics community for the last 30 years. And I'll talk about that. So I'll talk about vision-based localization and mapping. Again, because vision is cheap, we focus on using vision. Then I'll talk about other optical navigation solutions, which is actually something we announced yesterday as a product. And I'll give you an overview of that. And then finally, I'll talk about our architecture, the software development platform. So localization, as I said, is to provide GPS capability for the robot. It's a key capability. If the robot doesn't know where it is, then it will not know how to get to locations it wants to go to. So if the robot doesn't know how it is, it won't know how to get back to its charging station, which is one of the key capabilities for any autonomous robot. Because as soon as the robot runs out of battery, it's not able to go back and charge itself, it's dead. You have to go and find it, plug it in, and so it's not autonomous anymore. If the robot doesn't know where it is for vacuuming, then it has to do random motion because it doesn't know where it is, it doesn't know where it has been. So if you want to do complete coverage of a room, you resort to random coverage, which is what Roomba and evac and all the other robots in the current market do. But if you had localization, they could do systematic coverage and clean every spot once, and then move to the next room and clean that spot, and when they're done, they could go back and recharge themselves. So that's very core capability. And it's been a very long-standing challenge. So as I said, for the last 30 years or so, people have been struggling with this problem. And about 5 to 7 years ago, mainly driven by Carnegie Mellon, there is some research that started showing solutions to this problem. So Professor Sebastian Thrun, very well known, he's probably the guy that is associated with solving the SLAM problem, solved this problem using statistical techniques. The solution he had was using a laser rangefinder, which is a $5,000 device. It's a device that scans in one plane and gives you very fine range data, a profile of this room basically. And then what he would do is he would take a scan, take that scan, move the robot a bit, take another scan, and then stitch the map together. But obviously, he has to rely on the scans to match them against each other to know how far the robot has moved, because if you only rely on odometry slips, and then your map starts getting distorted. So that's where the simultaneous localization and mapping comes from. So you build a map to localize. When you localize, you can improve your map, and when your map is improved, you can improve your localization. But that was a solution that cost $5,000. Obviously, not a solution for consumer products. So we came up with vSLAM, which is using the same idea but using pattern recognition, visual pattern recognition. Imagine the picture that I took of this scene. Imagine that was taken by the robot itself. So when the robot comes here, it takes this picture, moves on, takes another picture, and so on. So it has a collection of pictures of this room. Every time it sees any of those pictures, it knows what picture it is. The next puzzle is, how do I know where that picture was taken from? So what the robot can do is combine the camera with odometry information, which is basically looking at the wheel rotations and gives you an estimate of how far you have moved. And the problem with odometry, pure odometry, is that especially on carpet, but on any surface, the wheels slip, and so you accumulate error, and you will get lost sooner or later. But if you combine that with vision, so I could start here, take a picture. I know, per definition, this is where I start. This is my origin of my coordinate system. I take a picture here. I move a bit and take another picture. So relative odometry, when you move short distances, is not that bad. So then I move a little bit more and take a picture, and I'm estimating my position based on odometry. But when I come back and see this picture, I combine the visual feedback with my odometry, and now I can estimate the position of those landmarks, the visual landmarks, better, and I can use that to better estimate my position. So it's bootstrapping. So it takes a little bit of a map, uses that map to improve its localization. When localization is improved, your mapping becomes better, and you bootstrap. So here's a video. Oops. I guess there is a video, yes. So here's a video I'll walk you through, which shows an experiment. The map you see up there is just for reference. It's manually drawn in. It's not used nor generated by the robot. The view you see on the left-hand side is the current view seen from the camera on the robot. On the right-hand side, you will see images appearing which correspond to the landmarks that are being recognized. And the blue circles are the landmarks which are being actually generated by the robot itself. So it just created a landmark over there, created another one over here, and it continues. The paths, the green one is odometry alone, and you will see that will slip over time because of slippage. That will drift over time. The red one is the path that is estimated based on SLAM, which is combining the vision and odometry. And you see the robot recognizes the landmarks and uses that to estimate its position, but also it uses that to estimate or re-estimate the position of the landmarks. Pay attention to this circle here. When the robot comes back and recognizes that landmark, that circle will shrink. So the size of the circle corresponds to the uncertainty associated with the estimate for the position of that landmark. And first time the robot came around, it made one turn here, second turn, and third turn, and then it created that landmark. And we know based on modeling of the odometry, so you can have statistical models for odometry, we know from there that when the robot turns, it accumulates most of the error there. So after 3 turns, the robot knows that its sense of position is pretty bad. So when it creates a landmark, it knows that the uncertainty of that position is large. But next time it comes back and sees that landmark again, it combines that visual information with the past history and can have a better estimate. That's why the size of the circles shrink, which basically corresponds to improving the map over time. And then other things you can notice as the video moves on is that it's able to recognize the landmark from different views. It will even, in some sense, you will see people standing in front of the camera, and it will be able to recognize the scene despite the fact that now there is a person in front of the camera. There was one case right there, that there is a person in front of the camera that wasn't there when the landmark was created. So in that sense, it's again, because of the visual pattern recognition, it's a reliable algorithm to work in real settings, real environments. No. So in this experiment, we actually manually drove the robot on a line we had taped on the floor, so we had the ground truth. But in the implementation on our, for instance, our software development kit, you put the robot down, turn it on, and it will do random exploration until it builds the map. So now you could ask me, how does the robot, so when I create a landmark, how do I estimate the position of the robot to that landmark when I recognize it? Only using one camera. And the answer is simple. We are actually using structure from motion. So when the robot moves, when I want to create a landmark, so as the robot is moving, I take 2 or more snapshots of the same scene, and I use my SIF features to do correspondence between the multiple images, and now I can estimate the structure of the scene up to scale. And the scale comes from the relative odometry that tells me this is how far you moved between these pictures. And when I combine those, now I have the structure of the scene, which means that I have the 3D position of all these SIF features is estimated. So next time I come around and recognize this landmark, I map my SIF features onto that structure and can very accurately estimate the position of the robot. So now I have 2 pieces of information for position. One is my relative position to that landmark, and the second one is odometry. And that's where you fuse this with maximum likelihood and can improve your map and your position estimate. So here's an example where this is the picture of the landmark. This is where the robot is, and you can see here the robot is closer to this structure in the background. It finds the corresponding points using SIF, nearest neighbors, and I can do triangulation and find the position of the camera here relative to where this picture was taken from. So I have relative pose estimates. So you could think of it as visual odometry.
It does something.
I cannot say, unfortunately. It's confidential information. So here are some examples of landmarks. Actually, this was in my own home, showing that in natural lighting with backlighting coming from the windows and so on, even one of the challenges was, this was one of the very early experiments. We have leaves and a lot of structure that is not stable in the background. And obviously that causes problems. So if, let's say, I have created a landmark of this window, most of the structure comes from this tree, and the tree is going to move around and the leaves are going to fall, so the structure is not stable. Then what the robot will do is when it comes back to that location, it doesn't recognize the landmark because it has shifted so much. it will just create a new landmark instead. And then there's a garbage collection that goes and looks at landmarks that have not been used for a while and just deletes them from memory. Yes?
How were they chosen in the first place?
Okay, very good question. So the robot has an estimate of its position uncertainty. So that's the covariance of the position estimate. So when the covariance of the position estimate grows large, beyond a certain threshold, the robot decides that I need to do something about my position estimate because I'm getting lost. So it tries to create a landmark. So then at the time, it will try to sort of anchor itself into the physical world. So it takes a picture, creates a landmark, and uses that as a reference to contain its position uncertainty. Because now that I've created this landmark, I can use that as a reference to position myself. So what in effect happens is that when the position uncertainty grows, I will create a landmark. The reason that position uncertainty started growing in the first place was because there were no landmarks I could use to localize myself, right? So it will only create the landmarks and distribute the landmarks as necessary in the environment.
At that point, how do you eventually figure out where, get a good position, a good idea of position given that landmark if you didn't know where you would?
So you have an uncertainty associated with the position when you create the landmark. But when you see that landmark, relative to that landmark, you get a very accurate estimate. So if I create the landmark here, this is my position. I create the landmark. When I move relative to that landmark, I still look at that landmark, and I know exactly how far I've moved relative to when I created the landmark.
So it's not reconciled with the map at that point?
It is reconciled. So in the map, you have the position uncertainty at the time you had when you created the landmark. You associate that with the pose of the landmark, right? And so when you move on, now you have a bound on how uncertain you can become relative to that landmark. But obviously, if you continue moving in this direction without seeing any of the previous landmarks, your uncertainty can grow unboundedly because you're accumulating error, similar to odometry. It's only when you go back and revisit some of the older landmarks that you can sort of bound the uncertainty. And what you do is actually when you close the loop, this is typical SLAM problem. When you close the loop, you backpropagate all of your errors across all the landmarks that you have revisited. And that's what tightens up the map. So if you go on a straight path, and despite the fact that you see hundreds of landmarks, this map will gradually deform until you go back and revisit one of the landmarks, and then you can constrain it and set it back in a correct form. So now, so when we developed vSLAM, we felt really proud. Because now we had gone from a $5,000 solution to something that was using a camera, but the computation was pretty heavy duty. So we were at the time running on a GHz Pentium. So we decided we need to develop an embedded board with low-end computing and optimize the algorithm to run on that. We did that, so we felt even more proud. Now we had a $100 or less solution. But as I talked about the example, the $200 solution vacuum cleaners, $100 for just localization is not a solution. It's a solution for higher-end robots, for security robots and so on, and there are some customers that we have in Asia that are interested in using it. But the bulk of the market today is at 200 to 300 vacuum cleaners. And if we want to capture a piece of that pie, we needed to have an even better solution, an even cheaper solution. So we started thinking about how can we relax the requirements so that we can have a cheaper solution. And then we came up with Northstar, which we actually announced yesterday. And this is a very simple solution, but very effective, and actually surprisingly novel. So the idea about Northstar is simple. So you have this beacon. It's an optical beacon. You plug it into the wall outlet, like here. And what it does, as it's doing right now, it projects two invisible spots on the ceiling. So it's infrared patterns it's projecting on the ceiling. So that's what you see on the drawing there. And then there is a optical sensor, and this is the prototype for the sensor, that is on the robot, looks at the ceiling spots, and uses that to triangulate and find its position very accurately and very reliably. So now, and this is an idea we had about a year ago and actually just announced it yesterday. So in big quantities, 100K quantities, we have a $30 solution that we can put on the low-end robotic vacuum cleaners. So this opens the market for robots at that end to be really intelligent and autonomous, to do localization and mapping, systematic floor coverage, going back to charging station, scheduled to go on a route from room to room.
So are those two circles different, and each room can have a different pattern?
Yes. So each of the if each of the spots is generated by 4 LEDs, it's 120 milliwatts of energy we are spitting out there, and each of them have an encoded pattern, and so they are unique. So the combination of those could be define a room ID for you, and so each of the rooms that have their own projectors have their own unique ID. And for instance, on this projector here, you can set the ID by this dial over here. So you say room 0 up to room number 9. And then the sensor basically, and then you could use more spots. You could put 3 spots out there and do 6 degrees of freedom estimation. In this case, we are talking about a robot that moves on a plane. We only need X, Y, and heading. So, and now, beacon-based solutions for localization are not new. In the factory automation and so on, people have for many years thought about using this kind of techniques, and there's a bunch of them developed. And the problems for beacon-based solutions, the main problems are 2. Number 1, installation of these systems has been hard, because typically what they require is that you have these beacons installed on a ceiling or walls or around the perimeter of the room and so on. And it's hard to maintain, costly install and costly to maintain. Number 2 is that the beacon-based solutions, especially optical beacon-based solutions, require line of sight between the emitter and the receiver. So you would have the projector be up there and the sensor be down here, and they could see each other. And if the robot went out of line of sight, that means it went under a furniture, or if the projector was down here, pointed in this direction, as soon as the robot was behind a chair or desk, it wouldn't see it. So the accessibility was constrained. So this simple idea of projecting the beacon pattern and on a surface and looking at the reflection solves both problems. Number 1, installing this is simple. It's like plugging an air freshener. Most people can figure out how to do that. And the second part is accessibility to this signal is available despite the fact that this is here and the robot is on the other side of the room. I'll be able to see the ceiling and localize. So, and actually, so we have a number of people from academia and research lab and so on that have been interested in this. And this is built for consumer robots. But we decided to have a developer version of this to sell for academia in small units. But obviously, the cost of that is going to be much more than $30.
So what about the issues of, would it work on this ceiling?
Yes.
And what about a vaulted ceiling?
Yes.
Or dark ceiling?
Yeah. So, okay. So one of the issues, actually, when we started thinking about this idea, we had to do a feasibility. And my red flags, or my feasibility questions were, number 1 was ambient light or artificial light interfering with the sensor. That was number 1. And the second one was saturation of the sensor. So even though you could encode a pattern that's unique on each of the spots, what if I was right underneath a spotlight with my sensor, so it saturates the entire sensor? So those were the 2 key ones. And obviously, variability of surface characteristics, vaulted ceilings, and all these things, height to the ceiling. These are all questions. But they were not major concern to me because they were more or less things I think we could solve with just boosting up the power of the projector. So the first couple of ones were the challenges, and we solved them. Regarding surface characteristics and so on, one of them is height to the ceiling. Because the signal we get is really very weak. It's 120 milliwatts, and we are reflecting off a surface. And then you have all this ambient light that's interfering, and you need to look for a unique pattern. And the accuracy of the system is directly proportional to the signal-to-noise ratio that you can extract from the signal. So with vaulted ceilings, I don't know what your concern is. Is it the height to the ceiling, or is it because the spots are on 2 different heights? Mm-hmm. The 2 different heights is not a big issue, because what the system will do is estimate the position of the spots, actually. So you can imagine this is on the robot, or you can manually put this sensor in this place, register the position, move it over here, register the position of the spots, and now you can calibrate it.
Okay.
So, or you could do it on the fly. If you have odometry information, the robot, as it's moving, it would calibrate. And actually, so think of it as SLAM, or think of it as a Kalman filter with the 3 states, which are the X, Y, and heading of the robot. And then for 2 spots, you will have 3 other states that describe the position of the spots. So you have a 6-state variable Kalman filter that you are constantly recalibrating.
In a room like this one, how many of those do you think you would need?
So for this particular one, I think the specs are saying it's a 6 by 6 meter room coverage for that. For this room, I would say you probably need 3 or 4 of this. But again, that's a function of the projector power. If we wanted to be able to see the spot from a larger radius, then we can boost up that. For some applications that we have already customers expressing interest in, for instance, factory automation or even supermarkets, big areas. They say, how many of these do we need? And the ceiling height is really high and so on. And we tell them we can boost up the power, and then you will be able to reduce the number of the projectors.
Did you have to address any eye safety concerns with projectors?
No.
Why, how do you reason about that?
Well, there are some, and I'm not an expert in this, there are some standards for what eye safety levels are acceptable and so on, and this is well beyond that. And this is UL approved as well. And we are going to do an FCC approval soon. Yeah. The power is really low, and then the effective power is even lower because you're modulating. You're on-off modulating the signal. So the effective power is much lower than the 120 milliwatts.
It's like a private remote control.
Yeah, basically. That's a good way to say it. Yes?
Do you see any trends in terms of merging technology? So, for instance, these location-aware kind of devices in the home that in the future, like merging this technology with security, which is already in the home, and it's wireless and it's motion-oriented, and piggybacking of those kinds of things, same thing with wireless, that's already now becoming very commonplace in construction.
Absolutely. I mean, we are open to any ideas of that sort. And as I said, this was developed mainly for low-end robotic vacuuming, but we can see the applications in other areas as well. Similar to with our vision technology, which was for robotics, but it ended up in retail fraud detection. So here are some examples of justifying the use of localization for systematic coverage versus random, but we don't need to talk about that. So I think I have 45 minutes, right? Or 15 minutes? 15? Okay, so I'll try to wrap up here so we have time for discussions. So the final thing is our Evolution Robotics Software Platform, which I said is sort of like the integrationware or middleware, if you will, which allows you to take a bunch of robotic components, hardware and software, and put them together into an application without having to build the infrastructure from scratch every time. This has been a holy grail for robotics for many years. NASA has had multiple million-dollar projects, multiple multi-million-dollar projects in this area. DARPA has, and still have. Universities have done a lot of this. Europe has this. Japan has this. Korea has this. So this is our version of that. And we have about 70 customers across the world, corporate and research, that are using this actually for development. So we talk about vision, navigation, and interaction. The architecture is the main part, but this is a software environment for development that has these component technologies, and also it has this infrastructure, which you could view as OS for robotics. And it consists of 3 major layers: the hardware abstraction layer, the behavior execution layer, and task execution layer. So hardware abstraction layer should not be any surprise to Microsoft. In robotics, this has been a major challenge, especially because there are no standards. You have tons of different robots, many different sensors, many different actuators, many different form factors. So this is where the robotic specific comes in. I mean, doing hardware abstraction for devices is something Windows does very well. But what is unique for robotics, or what is needed for robotics, is that the way the robot looks in terms of its geometry, its mechanics, its dynamics, its kinematics, determine how you write the software to do specific tasks. Just take a simple example for obstacle avoidance. So I want the robot to detect obstacles and plan a path to go around the obstacles. The algorithm depends on the shape of the robot. It can depend on the kinematics of the robot and dynamics of the robot. And the way the robotics community has developed these algorithms typically is that these assumptions are implicitly encoded in the algorithms to make them more effective. rather than generalizing and having a general planner that can work for any configuration of a robot, for any configuration of environment, and work for it. So what we have tried to do in the hardware abstraction layer is to sort of provide a common interface or use a standard interface for these kind of descriptions of the hardware so that the software modules can use that description to interact with the robot rather than hard coding those assumptions in the code. Other examples are the sensor placements. I mean, if let's say you have 3 range sensors, sonar sensors, that detect the obstacles, one pointing forward, one left, one right. The height of the sensors, the orientation of the sensors, and so on can all determine whether your obstacle avoidance will work or not. So again, these are things that are implicitly coded in the algorithms typically, but you don't want that to happen. So we have XML configuration files for each robot that describe basically these parameters using an XML language. And then you have a common interface. And on top of that, there's also abstractions of OS dependencies like threading and mutexing and all these things. But that's nothing new. And then on top of that, we have this thing called the behavior execution layer. And if you're familiar with the behavior-based approach in robotics, that's become a sort of trend in robotics for the last 10 years or so. People started with thinking about using planners, symbolic planners that were being used for theory proving and chess playing and a ton of different classical problems, and tried to use those for robotics. It didn't work out, and there's not enough time to go into that. The behavior-based approach is using a bunch of very dedicated modules. Each of the modules do a specific task, and then so one does obstacle avoidance, one does tracking of people, one does following a path, and so on. And then you need to coordinate their activities. So that's known as the behavior coordination or the action selection problem. So this layer allows you to deal with all those issues. And then on top of that, and one way to look at the behavior layer is that it provides you with continuous control or tight feedback loops. So you have perception and action, not much thinking in between. So it allows you to do tight feedback loops here. On top of that, we have a more discrete type of system, which is in that layer we view the world as a discrete event system. So events can be raised, and we have tasks that react to those events, such as Paolo walked in the door. Oh, there is a message for Paolo, so let me give the message for it. So this is a discrete event system. And so there's a tasking language up there. You can actually use C++ as the tasking language, or you can use Python for if you want it to be interpreted for rapid prototyping. And then the SDK comes with a bunch of tools to allow people to be more productive than hard coding all these things every time. So drag and drop capabilities to build up applications. Again, robotic specific tools. Here, computer vision is not the expertise of every robotics lab. So for simple things such as camera calibration can be a pain for people to do. So we try to develop algorithms where you can take a pattern like that, just show it to the robot by moving it around, and the robot just finds the features, correspondences, and then does the calibration and spits out the calibration parameters, and also tells you how well it thinks it calibrated. And then there's a bunch of other tools. Again, a lot of infrastructure to help you focus on your application rather than worrying about some things. So computational models of emotion. This is for entertainment robots, to be able to express emotions. So a robot that can become happy, sad, and interactive, playful, and all these things. With graphical personalities that you can display, voice recognition, text-to-speech, some gesture recognition, and a bunch of modules for for navigation, path planning, and so on. So a lot of infrastructure here. And then the benefits are obviously it's cross-platform. Each robot needs to have its XML file. Otherwise, if you have used those interfaces to interact with your robot, you could have your software run on different robots. For instance, our software runs on, we have 10 or so different robots in our lab, and the same software can be configured to run on any of those robots. So, and we already talked about this, and I will summarize by saying that we think the robotics market is emerging. It will take some time, but we are committed to providing some of the core technologies to help accelerate. And I think some of the key technologies that I talked about here for localization and mapping, beacon-based localization at very low cost and vision are some of the key things that I think are people are finding useful. And actually, that's my ultimate test, is not what I think is the right thing, but what our customers think is useful. And those are actually some of the key components that our customers are finding useful and using them in products. And the same thing with standards. So we are talking about this software architecture and a standard. As I said, it's been a holy grail. Many people have spent many $million on this and never really been successful. And I think the standards in this field will also be determined by de facto, not by mandate, not by consortia, by de facto. People will use what they find useful, regardless of how much mandate you have and how much endorsement you have of a particular architecture or not. So thanks for your attention, and I'll be happy to answer your questions.